everybody and good day. My name is Ali Farouhi Nejad from Faculty of Mechanical Engineering, University Technology Malaysia, and this video is a guideline for those students who has final year project. And if you are interested in the field of solid mechanics, this video explains the computational solid mechanics field and possible approach to solve a mechanical problem through this method. The objective of this study is to help students to get better understanding about the computational solid mechanics and several approaches to solve a mechanical problem. Prerequisite subject for carrying out a project in solid mechanics is static and solid mechanics, dynamic, strange material, and basic knowledge of the mathematics. The mechanical engineering divided into different branches such as solid mechanics, fluid mechanics, automotive engineering, aerospace engineering, manufacturing science, vibration and control. However, the solid mechanics field divided into three different parts: experimental solid mechanics, analytical and theoretical solid mechanics, and also computational solid mechanics because it's CSM. The experimental solid mechanics is related to the experimental test in the laboratory, and most of the time this kind of category is related to the material behavior and material properties extraction of different material in static cases or the dynamic cases. Moreover, the analytical and theoretical solid mechanics is related to the derived formulation and writing a computer code to developing different models in solid mechanics. However, computational solid mechanics is used because of the variety of the usage and application by different methods. Most of these methods is related to the iterative method if you study computational numerical method, and this method such as finite element method, multi-body dynamic method, and also discrete element method are in the family of computational solid mechanics. Here we have one example when we use a theoretical or analytical model. We write a MATLAB code in program and we want to see a trajectory of a projectile from one point, and when we are tracing one moving point and we want to know if we launch a projectile when we see one moving object, when we can hit by projectile, how we can draw the trajectory. By doing this, we write a code by some physical condition, some initial condition, and also write a solver and solving some ordinary differential equation. And then when we write the code as we have here, we run a code by defining some initial condition, then you can see how the projectile can move. But also, when we have some complex model, a very complex model, a dynamic system, we can divide this complex model into different phases. And these phases can be solved by some set of equations by ODE method, for example ODE 45 in MATLAB, and Then the result will be initial condition for the next phase, and at the end of the solving all this equation, we have the exact solution of one specific problem. Here you can see the result of some analytical problem by changing some physical condition. For example, in this case, we have two shifting system when we have a drag torque or when we don't have a drag torque, and how it is affecting on the performance of the transmission system. Or sometimes we need to define a very complex model, but we don't want to go to detail of every component, but we want to know the overall behavior of one system. Then we can use some lump analysis, and here you can see a lump model for a synchronizer element in the transmission in a gearbox. And if we run this kind of model after a few seconds, because this kind of solver is very fast than analytical or finite element models, and very easily we can connect the block diagram into the CAD geometry, and very easily we can see how the physical property can be transferred to a CAD model, and how the different situation can be observed over a lump analysis. And at the end of the simulation, also we can see the dynamic graph of different components, such as velocity here versus time, and also the force versus time in different simulation, and it is very useful when we have a very complex system. Also, the other application of the computational solid mechanics in academic and industry is related to the aerospace engineering, automotive engineering, railway design, impact engineering, product design, and also optimization and shape optimization and topology optimization techniques, and also to develop new material model in the continuum mechanics, for example, in fatigue, fracture, damage mechanics, and creep. Moreover, the most common method in solid mechanics and computational solid mechanics is finite element method. There are some possible ways to solve a problem through finite element method. First of all, using commercial software like Abacus, ANSYS, and Elastino. But the problem is, the license is not free, and you have to pay for the license. The other option is using open source software such as Codester or OpenFOAM. Or the last one is writing the computer code for simple geometry, one-dimensional or two-dimensional element. And most of the time, we use the third option for developing new finite element model to how to know what is the behavior of the new element that we derive. By the way, the chart of the simulation in every different approach is same. First, we have a pre-processing stage. Secondly, the solution or processing stage, and the last stage is post-processing. First, we define a problem, objective and target, and then we create a simulation model and generate a mesh, and if the mesh has a good quality, and then we can run the solver and then interpreting result, and if we meet the requirement, then we can say that the simulation was successful. Otherwise, we optimize the study by changing the mesh, checking again the boundary condition and so on. Here also we have three steps of final analysis procedure when we want to use a finite element package. For instance, in this step we have four steps, and the first step we define a problem considering the physical condition and requirement output to the problem. After that, creating the CAD generation model, and then discretizing the problem. It means that creating a mesh and selecting appropriate element type for each mesh, and then by considering the initial and boundary condition and also the loading and also predefined loading, sometimes the FEM model can be created, and then we transfer the finite element model into the solver that we choose. For example, we have a lot of solver based on different problems. For example, in a static case, we use implicit solver, or in dynamic case, also we can use implicit solver and also explicit solver. It depends on the degree of the complexity of the geometry and also the degree of the complexity of the loading. Moreover, in different cases, for example, in the vibration case, we use vibration and the dynamic model solver. For example, in dynamic, we have steady state or transient condition, and based on the application, we use the appropriate solver. Then, by using our selected solver and running the problem, we get some result, and after extracting the result, we have to validate this result. This result, through experiment or exact solution, can be validated. And if the validation part was successful, therefore we can say that our simulation and FE code was successful. Here we have some example of the academic and industrial application of computational solid mechanics. In aerospace engineering, to ensure the integrity of different part component or also the overall structure, we use finite element method by simulating different kind of experimental tests. Also in automotive engineering, we can simulate the body structure integrity or different component. For example, here we have one component and one component set in a gearbox, and we can simulating this. Or also we can pick only one component, single component, and we can see how the forces and moment affecting on the exact component that we selected. Also in the railway design, we can predict the life of the rail and the wagon and how it is affecting on the lifetime of the structures. Also in impact engineering, in different industry, for example in military or in crashworthiness of the car, or in aerospace engineering, the impact engineering simulation is very useful. And in faculty of mechanical engineering, many professors are focusing on this area. Also, in optimization and product design, we can use shape optimization, topology optimization, and predicting the life of one structure, and by optimizing the product, we can increase the life of the component as well. And here It was some introduction about the computational solid mechanics, and if you need any question, you can come to my office and ask me about your problem. Also through email, farokhi@utm.my, and from my phone number, you can ask your question about the computational solid mechanics. Thank you for your attention and have a good day.